Much like the semi-batch reactor, another alternative to the ideal reactors that's used to increase selectivity or to increase conversion in equilibrium limited systems is the membrane reactor. So similar to the case of reactive distillation in a semi-batch system, a membrane reactor could, for example, remove a product selectively from the reaction mixture, reducing its concentration and driving the reaction towards products. So as an example, let's look at the dehydrogenation of propene. So this is a strongly endothermic reaction. Which limits the equilibrium conversion at reasonable temperatures. So if you could run this reaction in a plug flow reactor with walls that were made of a membrane that were selectively permeable to hydrogen. So let's say I'm feeding here pure propane. So in my reaction mixture, I'm going to have some propene and some hydrogen. And so if my walls were coated with a membrane selectively permeable to hydrogen, I could remove it, therefore reducing its concentration and shifting the equilibrium further towards the product side. So if the reactor operates at steady state, we can write mole balances for propane, which we'll label here A, and for propene, which we'll label B, quite easily. So these are unchanged relative to the standard plug flow reactor. So the mole balance on A would just be the derivative of the molar flow rate of A with respect to volume is equal to the rate of formation of A. Similarly for B, dFB dV is just going to be equal to RB. So the mole balance on hydrogen here, which we'll label C, is modified since there's two ways that hydrogen could leave the reactor. It could either go out the exit or go through the reactor walls. So we can write the mole balance for hydrogen looking at a differential slice. So here I'll just draw a two-dimensional representation of our plug flow reactor, and we're looking at some differential cross-section. So we can write that the hydrogen going in by flow into this differential slice minus that coming out by flow minus that leaving by diffusion so that's hydrogen essentially going out the reactor walls this way plus the rate of generation of C, in this case hydrogen, is equal to 0 if we're operating in steady state. So writing this in terms of molar flow rates now, we can write that the molar flow rate of hydrogen coming into this differential slice, so at some position V along the reactor, minus the molar flow rate of hydrogen leaving at a position V plus delta V, minus the amount of hydrogen that leaves by diffusion in this differential volume, plus the amount that's generated by reaction in this differential volume is equal to 0. So dividing by delta V, and taking the limit as delta V goes to 0, we can write this now as the derivative of the molar flow rate of hydrogen with respect to volume is equal to the rate of formation of hydrogen minus the rate of diffusion of hydrogen. So assuming the reaction follows an elementary rate law, and the diffusion can be described by a mass transport coefficient times the concentration driving force across the membrane, we can write this out a little bit more completely. So we can write that the change in molar flow rate with respect to volume of hydrogen is equal to some forward rate constant times the concentration of propane minus a reverse rate constant times the concentration of propene times the concentration of hydrogen. And then we can express this diffusion again as a mass transport coefficient times the concentration of hydrogen at any point in our reactor minus the concentration of hydrogen on the permeate side, so on the other side of that permeable membrane. So this would be our differential equation for describing the flow of hydrogen through our reactor at any point. So in addition to using membrane reactors to improve equilibrium conversion, they can also be used to enhance selectivity. So for example, if we have a plug flow reactor with semi-permeable walls, where we're feeding some species to the front of the reactor at FA0, we could feed another reactant, say B, along the length of the reactor to keep its concentration low. So this is analogous to adding the reactant continuously in a semi-batch reactor. So what this would look like, essentially, we would have a distributed reactor where we have some total molar flow rate of B coming in, but it's being fed from a permeate side through the walls of the reactor through this membrane. Okay, so this has shown some examples how membrane reactors can be used to both enhance conversion in equilibrium limited situations, but also to enhance selectivity in an analogous way to the semi-batch reactor.